Today we are really glad to have Yuval Grossman visiting from Cornell University. Um, so I wasn't prepared for this one, but because I because uh, I know him pretty well because primarily because he's one of the leaders in our field, and I've been following his work for as long as I remember, and so I think I can just tell he's um, introduce him pretty easily. So the uh, um, Professor Grossman got a PhD from Weizmann Institute in Israel, and I would guess you were postdoc at SLAC in at the end of the last century. So I would guess you got PhD in 1996 or 97.
Nice.
Okay, yeah. So like I said, yeah, after a PhD from Weizmann, he was at the postdoc at SLAC for several years, and then then went back to Israel as a faculty member at the Technion, and then after staying there for several years, he moved back to the U.S. and to the Cornell University, where he's been ever since. And Yuval has been one of the leaders in the field of flavor physics as well as neutrino physics. For example, I still remember in one of the summer schools I went, Yuval was lecturer in the TASI 2002. Yes. So where I got exposed to neutrino physics at that time, and I still remember fondly of his lectures. And so so I know that the Yuval is a great teacher as well as great researchers. So without further ado,
Thank you so much. Is it good now? Yes. Okay. Thank you very much. I'm definitely so happy to be here. I mean, just when I come to give a Dirac lecture, I was like, wow, Dirac, you know. So for my students, I already from the beginning of the semester, I'm going to give the Dirac lecture. Wow. So you know, in the way here, I stopped. They said the Dirac library. I stopped. I took picture. I'm so happy, you know, just associate my name with Dirac. Anyway, so my talk, I'm going to talk about flavor physics and effective field theories. And always the bigger problem when you come and give a set of 2 lectures in a place that you don't know is the almost total, I have basically no idea what you guys know, okay? And that's always a problem because you try to be like exactly the right level, right? And you know how it is. If you talk too basic, it's like, come on, you're going to tell me F equals ma? I know that. So I assume you know that, of course. But I mean, and then if I talk too high, then you're like, very quickly everybody is losing me. And you can tell. I mean, those of you who teach, you know how it is. One day I want to do this library of student faces, okay? You all know what I'm talking about. It's like, wow, yeah, now they got it. And I totally lost you. Okay, so I hope I will not say those faces today. But since I know very little about your level, please stop me if at some point I will like, hey, you know, as we all know, and then say, no, actually, we don't know it. And I'd be more than happy. It's a blackboard talk, so I can go around. Most of what I'm going to talk is based on 2 things that are 2 of my writing. So the first one that I'm extremely excited about, it's a textbook that we are writing. Me and my former advisor, Yossi Nir, we are writing the textbooks. It's basically done. We are now at the level of working with the publisher about how exactly I should put references in, where the comma should go. So it's extremely exciting. But that's basically the final version in terms of physics. It's in this link. And if all goes right, good, in September we're supposed to have the one printed. And of course, you know, I'm going to follow much of what I did here. And another one is a review that I wrote on flavor physics that's based on some TASI lectures that I gave. It's again, it's like 150 pages, much, much more than I can cover. So if you want to know more, these are two resources that I definitely like, and you can go and see this. Okay, so as I was told, some of you are not doing high energy physics, so I want to start from the very beginning. And again, excuse me if it's going to start a little too early, but let me kind of move here to the middle. And let me ask the following question. Is like, what is high energy physics? So why are we doing high energy physics, and what is the big goal of doing high energy physics? Okay? Let me actually ask you guys. I love it, to have some discussion. What is it? I mean, you had been asked this question before, right? Sometimes you've been asked this question just by friends, right? Sometimes you ask this question by the dean of the school, right? So you really have to be ready with the answer. Please, 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 yes?
I don't know, I just say it's a fancy way of saying particle physics.
Nice. Yes. Actually, I really prefer the high energy physics because I find the particle physics, it's like, it's like when you're a writer, you say I'm a pen user. I mean, it's so particle physics are what we use in order to really get into high energy physics.
Especially if it's an elementary part.
Elementary part.
Oh, you're not doing the advanced part.
That I never got. No, but yes. But like really, what is our big dream? We all know the answer. I just want some discussion. It's so much more fun to talk an hour and a half and nobody answers. What? Oh, if we get a little interaction. The theory of everything. Yes. Okay. I kind of like it a little more ambitious than what I like to say. So the way I like to describe it is that as high energy physics, we try to get the fundamental law of nature. Okay? And if you kind of want to say what is the difference in high energy physics and say somebody who do condensed matter, is that there's two aspects of physics that are extremely excited. One is to find what are the rules, and the other is how these extremely simple rules get us to this amazing phenomena. Okay? And very roughly speaking, high energy physics asks the question, what are the basic rules? And then, say, condensed matter people ask, giving the rules, how we get this amazing phenomena. Okay? And it took me years to come to the shorter way of explaining what I'm doing, and the shorter way to explaining what I'm doing is this. I hope you appreciate it. Okay? So if someone asks me what I do, that's what I do. And then they said, oh, I don't understand this part. I don't understand this part. Okay? And the amazing part is that actually, by now we have a very good idea what is the Lagrangian of nature. Okay? But we also know that we don't know the full answer, which seems that there is a contradiction, but it's not. Okay? We know very well how to describe nature fundamentally. What is the fundamental Lagrangian of nature? What are the fundamental laws of nature up to some energy scale or up to some distance scale? But we know that at shorter distances or at higher energy, there's something deeper going on. We basically sure about it, and we are now, that's what we are doing. We try to understand what's going next. And the whole idea of effective field theory is very, very much connected to this question, how can we understand better than what we understand now? Okay? So what I want to do to start with, I want to start in explaining actually what do we know and what are how we are actually kind of understand what we are having. And then hopefully in my next lecture on Friday, I will get much more into the details of what's standing beyond and what we are trying to understand later. Okay? Any questions so far? We all know about this? Great, okay. So how we actually approach this question, okay? So you say, oh, I want to find what the Lagrangian is, and you can do it in many ways. As you all remember when you did analytical mechanics, it's a universal phenomena, okay? In analytical mechanics, when you take analytical mechanics, the professor come and said, L equal T minus V. You remember this? Yes? Did you ever had any professor who said, well, I don't know what L is. No, L is T minus V. We all know what L is. And then you may ask the professor, how do you know that it's T minus V? Anybody ask the professor why it's T minus V? Nobody, huh? because I know we are good students. You know, the professor said T minus V, all right, hell, T minus V, and then we are happy, okay? And the answer is why it is T minus V. You say, wow, this is really nice, because when you do the Euler-Lagrange equation, from T minus V you get F equals ma, and we love F equals ma, so that's why we choose T minus V, okay? Is it a satisfactory answer? Yes, no, maybe, no?
Maybe.
It's good enough, it's good enough. It's good enough, I love it. Yes, it's good enough. Well, of course, it's satisfactory in the following sense. We want to describe nature, right? That's only what we care about. So if we have a Lagrangian that describes nature, F equals ma describe nature, L equals T minus V describe nature, then it's good. But somehow, there's something a little deeper. You say, you know, can we get it from something more fundamental? Is there something deeper going on that we can get the T minus V? Okay? Yes? And when we do analytical mechanics and we get the T minus V, we kind of touch upon it. Okay? I mean, Landau-Lifshitz section 3, I'm not joking. Okay? They actually go through the explanation why actually the T must be mv squared. And if you never, or you don't remember why it is, it's a really cool. It's actually directly a result of symmetries. It's a result of time translation invariant, translation invariant in space, rotation invariant, and Galilean invariant. So if you impose those 4 requirements on a free particle, the Lagrangian must be some numbers times v squared. And this number we call m over 2. Okay? So that's Landau-Lifshitz section 3. And most of the time when we teach analytical mechanics, we kind of go fast over section 3 because it's a little too advanced in the beginning when we don't really know. Okay, but if you never go back to section 3, I really love section 3 of Landau-Lifshitz. Okay, so how do we do this? How we get the Lagrangian? So as I said, one way to do it is that we really want it to describe nature. Okay, and the other way to do it is that maybe there's something fundamental, much deeper, that can lead us to this. There's some symmetry principle that led us to this. Okay, and I'm sure you all heard about the fact that we use symmetries and all this. And let me be a little more formal how we do it. Okay? So the way we kind of built our Lagrangian, and the word that we use in high energy physics is model building. We build Lagrangian. We should have called it model designers, but it's an old-fashioned word, so we call it model building. And the way we are doing is as following. I say, hey, you want to design a model? Here it is. You go to a website. It's a model building designer. Okay, you click, and the first question the website is asking you, the first question is ask you is, please tell me your symmetry. What is the symmetry of the model? Okay, so you have to provide the symmetry. It's like choosing your design. You're choosing your color. Okay, I want to design a shirt. You say, hey, what colors do you want for your shirt? Okay, and the other thing that the website gonna ask you is, what are the fields in your theory and how they transform under the symmetry? Okay, and you just have to say, hey, I have the following field, and they transform like this. This is input. Okay, fields and their transformation. Okay? And I really want to think about it. It's really like designing whatever, a shirt. Okay? I say, hey, what kind of shirt you like? And you say, I like the shirt to have a symmetry, like left-right symmetry, maybe, you know, and this is an approximate symmetry here on my thing, right? And then you ask what it's made out of. And you say, I want it to be made out of cotton or for polyester or whatever. Okay? So you put it in, and then you have to give it to someone that there's some machine, and you get the shirt out of it. Okay? So that's what we do here. You give me the symmetry, you give me the field, I put it into the little machine, and the output of this machine is a Lagrangian. Yes, thank you. Okay? So then what we do, we say, once you tell me the field, the symmetries in the field, the output is the Lagrangian, and the way we are doing it is we follow something called, I think it's called the democratic principle. Okay? So let me describe to you what democracy is. No, I mean, it is. So in democracy, at least in utopian democracy, everything is allowed unless it is forbidden. Okay? That's why there's huge book of laws, okay? In a totalitarian regime, it's the other way around. Everything is forbidden unless it is allowed. That's why they have a very short book of rules, okay? But that's the idea of the democratic principle. Everything is allowed unless it is forbidden. So what does it mean? It means that I need to write all the terms in my Lagrangian that are allowed by this principle, that are made out of these fields and are invariant under the symmetry that I impose, okay? And if a term is not invariant, then it's not allowed and I cannot write it. However, if this term is allowed, I must write it down, okay? And then I write my Lagrangian, okay? And there's one last thing that I need to do, and the one last thing is something that, again, as physicists, we love to do. It's not that we love to do, we just do it all the time, okay? Is? That we do later. Is? Almost. So I write so if I can write, how many terms I can write? In principle, I can write infinite number of terms. So what do I do? What I need to do? Truncate, okay? It's the usual story, you know, when a physicist go in the street and the physicists meet a function, what the physicists do to a function, okay? You always, when you meet a function, what you do to her? You expand and truncate her, okay? I mean, you know it, right, when you go on the street, okay? But that's what we do in physics. You take what you have, you expand and truncate. So that's what we do for our Lagrangian. We write the most general Lagrangian up to some order, okay? And who decides what order it is? Up to what order? So in principle, the machine going to ask you, the website going to ask you how precise you want your Lagrangian to be. And what usually we answer? What is the usual answer for this? Dimension 4. Usually we say up to dimension 4. Why dimension 4? For renormalization. Very nice. So that's part of the reason that I'm here, because renormalization. So let me just say, okay, for those of you who don't know, you usually say we write the Lagrangian up to dimension 4. And the reason, the usual reason that we are always giving to this answer is that we do it up to dimension 4 because dimension 4 are renormalizable Lagrangian. That is, it's a Lagrangian that is mathematically consistent. Dimension 5, and when I say dimension, even, you know, it's just a language. Coming back to mechanics, mechanics is just when you expand in x to the n, it's the n. So up to n equal 4. It's the usual thing. Okay, we just call it dimension in particle physics. But we go up to dimension 4 because up to dimension 4, the theory is mathematically consistent. When I go to dimension 5, the theory is not mathematically consistent. Okay? And the more formal name for this is renormalizability. Okay? So then we go up to dimension 4. However, and that's part of the reason you invited me here, is to talk about effective field theories. And effective field theories are fundamentally, we don't really care if they are mathematically consistent all the way to infinitely short distance. And I know that David Kaplan had been talking this morning a lot about these kind of things. So hopefully we understand what I mean. I really don't care about going to infinitely short distance, okay? Because all I care about, not all I care, but I care about, say, what's going on the LHC. And the LHC is not going all the way to 0 distance. The LHC, you know, sometimes at 10 to the minus 20, they stop, okay? So I don't care. 10 to the minus 20 centimeter is considered large. And I don't care what's happening at 10 to the minus 30 centimeter, yes? Okay? So therefore, there's no fundamental difference to actually stop at L equal 4, okay? We keep doing it. And the way I like to think why we're doing it at dimension 4, because so far, all the experimental data, almost all the experimental data, had been explained by going to dimension 4. And that's, if you like, is the way that we learn it really from the very beginning. You have a system, you expand, until you get the sensitivity compared to the experimental results, right? So if your experimental result is 1%, you need your theory to be accurate at 1%. So what we find out is that, as of now, the standard model, our theory from this Lagrangian, when we go to dimension 4, explain almost everything, okay? So therefore, we kind of stop at dimension 4, but now we actually kind of going up in going in higher dimensions, okay? Any questions? Yes?
This way you'll never be dealing with things like the Sine-Gordon model.
Yeah. So that's exactly the point. So of course, you know, there's so many ways to go around here, okay? And one way is, I don't want to say the wrong way, is just say, you know, I really care about renormalizability, and I really want to do everything in dimension 4, and I really want to understand if I go to something deeper, I want to have always a full renormalizable model, okay? And another way, and that's the way I really like to think, and that's the way I'm going to proceed here, is I said, I really, really love to go to higher dimension operator because as long as I need them to explain the data, I'm totally fine. And I defer the question, what is the fundamental theory, to later. And it's totally fine to defer questions, okay? We cannot solve everything at once. So I totally agree. It's somewhat philosophical where we want to go. But in particular, since you invited me to give about effective field theory, I will go in direction of effective field theory. It's non-local, and we have other issues here.
Okay.
You also had a question?
It's like the infinite series.
So, okay.
Yes.
My intuition is why we went up to dimension 4 is because, I mean, as far as we can tell,
Yes.
we are in 3+1 dimensions.
Yes.
And I understand with effective field theory, we're dealing with operators and we scale it to 4 dimensions to keep
Yes.
Lagrangian correct. But my intuition was, it just so happens that dimension 4 theories are, for the most part, normalizable in some cases.
Yes.
And that just so happens to be a very nice property of them. But the reason we go up to 4 dimensions is because we live in 4 dimensions.
So let me say, the word dimension, it's a really somewhat unfortunate use of this word. When I talk about 4 dimension, that's 4 dimension of space-time. That's what we really should call dimension. What we should have called this, we should call it the order, the expansion order. Okay, so yes, about mass dimension is the x to the n that I expand. Okay, so the fact that L equals 4, that it's happened at D equals 4, it's an accidental. And in 6 space-time dimension, actually phi to the 4 is not renormalized. I mean, whatever. Anyway, so the point is that we understand how we are writing Lagrangian, and we have to provide the symmetries, the fields, and we write the most general one, and we truncate it at some point. Okay. Any more questions, remarks? Yes.
But you need to talk about symmetry breaking and the nature of the low energy state when you define 1 and 2.
Yeah, of course. So this, sometimes we actually define property number 3. I didn't want to get into. And property number 3 is exactly the spontaneous symmetry breaking pattern of the theory. Okay? I just didn't want to get into too much here. But of course, there's so much more, and I tried to be a little brief here. But you're totally right that that's what we need to do. Any more remarks? Catching me on all this?
In some sense, restricting yourself to perturbative field theory.
Absolutely. So the way we are doing it, we are doing perturbative field theory, and in some cases we know this is not going to work. Okay, and for yeah, so yes, so and even right now, but I really want to talk a little more about QCD later on. Okay, so there's definitely so much that I skipped, and as I said, because I wasn't sure at what are the level of everybody here, but you are catching me in a lot of corner that I cut, but definitely there's much more to the story. But this is kind of what I like to think. That the main idea of the story is this, writing the Lagrangian and cracking it. Okay? So now I want to discuss about flavor physics, and many parts of flavor physics, this is enough for us. That's what we need. Okay? And then we can actually go, and hopefully on Friday I will go into some parts that we need a little going beyond it. Okay? Okay. So let's write the standard model. So in principle, I can do everything, any model that you want. And then as an example, we choose the standard model. I don't think I ever seen anybody give another example because it doesn't work. So as an example, we do the standard model. So what is the symmetry? All together now, we all know it, is SU3 cross SU2 cross U1. Okay? And I'm sure you heard about it. Even if you don't fully understand and appreciate all the details, I assume that all of you seen the standard model gauge group, and we assume it's a local symmetry, and it's a gauge symmetry, etc. And that was point number 1. And point number 2 is what are the fields in the standard model and how they transform. So the field of the standard model is really a lovely name. They call it kind of cute, right? Qdl. And the Qdl fields of the standard model, they are the Q, U, D, L, and E fields, and each of them have its own transformation property under the symmetry. For example, the Q transform as a 3, 2, and a 6. If you know what I'm talking about, then you say, obviously. If you've never seen it, then I'm not going to explain it to you. I'm just going to tell you that this is really satisfied this point. Okay? Just like that, when we say that in analytical mechanics, when we have a particle and the position of the particle transform like a vector, that's just a generalization of this statement. Okay? I'm just leave it like this. Okay? And one very important point is that in the standard model, I choose to have 3 of those. Okay? So times 3. So I take 5 sets of fields. Okay? I said a set of 5 fields, and I choose 3 copies of them. Okay? And this factor of 3, that's what we call flavor physics. It's really the fact that we have more than one copy of those fields that made out the standard model. The fact that we have 3, that's consistent of the whole point of flavor physics. Okay? And all of these are fermions, I forgot to mention. And then there's also one scalar of the standard model. It's called the Higgs field, and it transforms like this. But it doesn't matter. But this one, there's only one. Very important. Okay? Times 1. Okay, that's it. I'm done. I defined the standard model. What I need to do now, all I need to do now is put it in this machine and write the Lagrangian. Okay? And as I said, in our book, that's we define actually the beginning, and then it takes 200 pages, and after that we have it all and we understand what's going on. Okay? So it's not a trivial, you have to explain some things of going on, but in principle it is trivial. In principle, there's nothing crazy going on here. You take it, you write it down, you involve spontaneous symmetry breaking, you gauge bosons and quarks masses, etc., etc. But fundamentally, everything here is kind of straightforward field theory. Okay, there's nothing if you like, about particle physics going on here. Okay? Yes?
So, okay, this is a quark doublet, up-down, left-on doublet, electron. So up-down, right-handed up-down.
Yeah, so I can write it explicitly if you care. Yes? Okay, yes. So Q left is a doublet of SU2, and after spontaneous symmetry breaking, we write it as U left and D left. Okay? Then the U is a U right field. Okay? The D is a D right field. So this is something like the up charm and top. This is the down strange and bottom. And the right ones are separated. And the L is the neutrino and the electron. And the E is the electron right. That's the left-handed part. Okay? Good. Good that we have the thing. Now, the point is that at this point, we cannot really tell the up and down component. We will tell them only after we have spontaneous symmetry breaking. But again, I'm not really getting there. Just from lack of time, I try to be a little brief here. Now, I like to explain one very important concept in general in physics, and in particular in particle physics, and that's the difference between a standard model, and I think when you shouldn't read it as S, not ASM, because then it should be an N. It's a standard model versus the standard model. So what is the difference between a standard model and the standard model? Okay? So the point is that any model that we write, any Lagrangian that we write, have some number of physical parameters, right? So coming back to mechanics, if you have a Lagrangian of, say, harmonic oscillator, you have the mass of the particle and the spring constant, K. So there's 2 parameters that describe your simple harmonic oscillator in mechanics, right? How do you know those 2 parameters? You need to measure them. Yes, they are not given. So when you write a Lagrangian, the Lagrangian involves the number of parameters, but there's no notion of the value of those parameters. In order to know the value of those parameters, you need to make a measurement. Is that clear? Yes? Let me just say here a semi-philosophical point that is a little deeper. the parameters themselves, in a way, are not physical. There's no physics in the value of the parameter. Physics is always about making relation between different sets of experiments. And the parameters are a very useful bookkeeping tool to do it, okay? So think about a very simple experiment that I can do right now in front of you. And I ask how long it's going to take for this thing to fall down versus how much it's going to take for this one to fall down, okay? The physics is, so the way we are doing it, we say, oh, I do this, I measure G, and then once I measure G, I know to predict this one, okay? But what we are really doing is that we are saying the result of this experiment is the input for the next experiment, okay? Everything goes through experiment, okay? So if I have a theory with two parameters, I need to do two experiments, and based on the result of those two experiments, I make a prediction for the rest. The way we do it is to say I made two measurements. Those two measurements I interpret as measuring the parameters, and then I make prediction. But fundamentally, the parameters are not physical. They are actually result of other measurements, okay? So now we can come back to the topic of what is the difference between a standard model versus the standard model, okay? A standard model is a generic theory, or any of those theories, independent of the value of the parameters, okay? The standard model is that theory where the value of the parameter are the ones that are given by nature, by the real world that we are living in, okay? Coming back to the simple harmonic potential, I can say a simple harmonic potential is the one that is whatever it is, you know, p squared over 2m, that's the Hamiltonian, mv squared over 2 plus kx squared over 2, that's the generic Lagrangian for harmonic oscillator. Now you take a specific one, okay? I take something that's, and I measure and I say, oh, when omega is equal this and the mass is equal this, that's my very D simple harmonic oscillator that I'm working in. Is that clear? The distinguish between those kind of things? Very good. And the reason that is so important is that there's some predictions, some results that we see in nature that are a result of a standard model. They are there in any standard model that I have, independent of the value of the parameters. However, there's some other results that we see in nature that are very specific to the values that we see in our nature, okay? That things are, it's going in nature. And what it's turned out is that in many parts of the standard model, the specific value of the parameters are not very important to the result that we're gaining, okay? When you look for Higgs physics, for example, or precision, the gauge sector of the standard model is not very important. In flavor physics, however, it's turned out that this standard model it's very different than a generic standard model. The value of the parameter are far from generic, and that gives us a lot of very interesting results. And as we go, and we're going to talk in general flavor physics and about effective field theory, this distinguish become important. Okay, sorry about it. Are we okay with this? Yes? Great. Okay. So, now that we made all this, let me write the Lagrangian. Very schematically, I want to write the Lagrangian. And let's write the Lagrangian first up to dimension 4, because that's what we always do, and as we already discussed, there's some reason to do this. So the standard model Lagrangian up to mass dimension 4, I can write it as following. And actually, it's not only the standard model. Any Lagrangian up to dimension 4 can be written in the following form. I can write it like this: L kinetic plus L phi plus L psi plus L Yukawa. And let me explain what I wrote here, okay? So what I'm saying is that in general, any Lagrangian in 4 dimension up to mass dimension 4 can be written as a sum of 4 terms. And what are those 4 terms? This is the kinetic term of all our fields. It involves the kinetic terms of the gauge boson and of the fermions and of the scalar, okay? This term, also known as the scalar potential, is a term that only involves scalars, okay? This term is a term that only involves fermions, and in particular, when we go up to dimension 4, this term is only corresponds to mass of the fermions, Okay? Here it gives us both interaction and masses for the scalar. This one gives us only mass for the fermion. And this one is called the Yukawa interaction. And the Yukawa interaction is something that involves both scalar and, and fermions. And in particular, it can have only one specific form. And the specific form is phi psi bar psi. Let me write it. Phi psi bar psi, where psi bar psi are the fermionic field, and phi is the scalar field. Okay? And that's called the Yukawa term. Okay? So let's talk a little bit about those terms. Okay? So the first terms I want to questions? Yeah.
Is there a reason for just leaving out like bosonic fields here?
So the bosonic fields are here. So the way, again, so the way is that we know, very general about quantum field theory in 4 dimension, is that the only way you can get a bosonic field are scalars, which are spin 0, and gauge boson that are spin 1. The gauge boson must have only kinetic terms. They cannot have mass. And the scalar, you can write basically everything, and that's the scalar potential here. Okay? In the standard model, so that's very generic. In the standard model, it's turn out. What does it mean, turn out? I mean, based on the input that we provide on the website, okay? It's turn out that this one is 0. The fermions do not have mass at the Lagrangian level. They get mass eventually through the Higgs mechanism, all those kind of things that I'm not going to get into much discussion. Okay?
Is that part of your symmetry?
Yes.
Okay.
So it's part of the way I assign my field under the symmetry. Okay? So it was also, of course, done by construction. Okay? Because we kind of understood that we need things to be done through the Higgs mechanism, etc. So we did it like this. Okay? And the kinetic term, basically here, everything is set by the symmetry. There's almost no free parameter. The only parameters that are free are the gauge coupling, okay? And they are basically given by the following names. Very deep, nice names. G. Anybody know why G stands for coupling? It's kind of a very interesting story, okay? It starts from Newton, that he wrote G for gravity. And then when we move to the weak interaction, then we call it G Fermi because it was still G, okay? And that was the capital G. And once we understand that the G Fermi is actually an effective operator that's coming from small thing, then the capital G of G Fermi becomes small g of coupling, okay? So this G is because of gravity, and of course the only thing that it doesn't explain is gravity, okay? So G strong is the coupling of the SU3 for the strong interaction. G is the coupling of the SU2, and G prime is the coupling of the U1. As I said, very nice, useful name. In general, they are coupling constant, okay? And they are not in particularly small or anything, okay? L phi is the part that gives us the only one scalar in the theory. So the L phi is also called the Higgs potential, or the scalar potential. And it's actually kind of very interesting. It's the so-called double well potential or Mexican head potential or whatever. And that's what gives us spontaneous symmetry breaking and give us mass for the gauge boson and mass for the fermions. And I'm not going to talk about it, but that's called the Higgs potential. The Higgs potential. Okay? Very nice. And this one, we're going to spend more time on it because that's where flavor come into the game. Okay? Because this is where actually we start have the play between the fact that we have three copies of this QDEL play a role in this term. Okay? Very good. Okay, so if you've seen it before, you know exactly what I'm talking about. If you don't, hopefully at least you have some idea what I'm talking about. I know I had to be really fast. And now what you want to do, of course, that was up to dimension 4. I can keep going and go to higher dimension. And these are effective terms. So it's turned out that when we go to dimension 5, there's only one extra term that I can write when I go to dimension 5. So L d equals 5 of the standard model. There's only one term. And the term is, roughly speaking, I'm not writing it very precise, is LLHH. Okay? And since it's a dimension 5 operator, that means that the coefficient in front of it have to be suppressed by some mass scale that we call lambda, and by assumption, this lambda is very high. That's by assumption. We doesn't have to be the case, but we are following this assumption. And this term, at the end of the day, give us neutrino masses. So this gives m neutrino not equal to 0. So here, the neutrinos are massless at the fundamental dimension 4. When we go to dimension 5, the neutrinos have mass. Okay? So that's actually a really, really nice example why I like to go to dimension 5. Yes?
What does the L to the H's mean?
Oh, shit, I was not precise enough.
I mean, just generally.
Let me be more precise. You know, sometimes I'm so used for this notation and I jump between them without noticing that I was doing it. Okay? This L is the lepton field, the neutrino, and this phi is the scalar that have the Higgs boson. Okay? And I kind of jump between phi and h, and I should not. I should be a little more careful about the difference between them. Okay? So one thing that I really like about this, and again, thinking about the effective field theory approach, is that one way that we describe why we want to go up to dimension 4, and we say, well, explain everything we've seen. But then, just like it's really, you know, physics 101. We say in physics, you have your theory. Once the theory is not working anymore, you go higher and higher precision. You also need your theory to go higher and higher precision, right? That's what we do. You work, then it's not enough. You go for higher order in your calculation, right? That's what happened for us. If you think that's 30 years ago, the neutrino, everybody was, there was no evidence that the neutrino have mass. Okay, so you go up to dimension 4. Then basically, now we're totally convinced that neutrino have mass. What you need to do, go higher order in your calculation. Go to dimension 5. You go, and boom, it's explained it. It's very simple. Of course, I totally oversimplify the situation. But fundamentally, that's what happened. I go to dimension 5, and I get neutrino mass. Okay? Now what's happened at dimension 6? Dimension 6, it's a mess. It's a mess. Why? Because dimension 6, I can write 4 Fermi operators. So in general, in dimension 6, I can write something like Q, 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 Q. I can write something like Q, 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 L. I mean, Q, 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 I cannot, but I can write things like Q, 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 L. I can write so many different operators. Dimension 6 have much more operators than all the standard model before it. And if I say, let's check this, the most general thing, this is a mess. In particular, this operator results in proton decay, and the proton is rather stable. Okay? I mean, we believe it must decay someday, but maybe not in our lifetime. Okay? So it's a big mess. So actually, what we are seeing is as following, kind of interesting. Up to dimension 4, it's explained basically almost that we've seen. Okay? Dimension 5 was kind of a blessing. Actually, it gave us something. It predicted very small neutrino masses. And boom, you know, we found them. We go to dimension 6, and dimension 6 basically tell me it have to be extremely small because it predicts basically very bad things. Okay? So if I just write dimension 6, it's ruled out because it predicts proton decay, and the proton is stable, basically. Okay? So there's something weird going on. And it's all related to the question of the difference between S standard model and S standard model. The assumption here is that everything is generic, but what we see is that our standard model, the standard model in the real world, is not generic. It has a very specific structure.
So is that the dimension 5 operator breaks the renormalizability of the theory?
Exactly.
And we don't care then anymore.
So of course we do, but I don't care. But we really care. So what we are doing is that we try to find a lot of models that this is the effective field theory description of those models. And those models come usually under the name of a CISO model. If you heard about this word. Yes. It was very useful for me because I didn't know what a CISO is. And only through physics I learned. And when I moved to the US and I went with my kids to the playground, I said, yes, physics is useful in everyday life. Okay? So those CISO models are actually the full dimension 4 renormalizable model that at the low energy effectively described by a dimension 5 operator. Okay? But there's actually other ways to get this dimension 5 operator. Okay. Good. Any more questions, remarks?
So the neutrino mass given by this operator, is that a Majorana mass?
Yes, totally.
Why doesn't it give the electron also a Majorana mass?
Oh, so the electron cannot get a Majorana mass because there's a symmetry that protects it.
Yes,
Okay. But this symmetry, so the fundamental difference between the electron and the neutrino is that in order to have a Majorana mass for a particle, it must be neutral under all the unbroken symmetries, okay? And the neutrino is charged under SU2 and U1, but the SU2 cross U1 is broken, and it's broken into electromagnetism. And electromagnetism, the neutrino is not charged under electromagnetism, but the electron is. So that's why the electron cannot get a mass, and the neutrino can.
So this dimension 5 operator respects all those symmetries?
Of course,
Okay.
totally. So I should have said, when I write the most general Lagrangian, the democratic principle works to all orders. It's the truncation that we do, okay? Yes?
But presumably, though, it's possible to have a deeper theory whose symmetry is completely different from the time models.
Exactly.
And you can imagine a theory in which, when you expand it to lower energy, there isn't this dimension 5.
Totally, absolutely,
Right.
totally. So the point is as following. When we are doing with, and I wanted to talk a little bit more about it on Friday, but since you asked, let me kind of expand a little bit on this point. The way we are thinking about when we write the higher dimension operator, we are following the democratic principle. The democratic principle tells us everything that you should write, okay? However, when we go to higher dimension operator, the democratic principle may not be valid because it might come from some deeper theory. Up to dimension 4, we say this is the fundamental theory. It's renormalizable. We believe this is the fundamental theory. That's why we should write everything. When we go to dimension 5, the assumption is that it's generic and I follow the democratic. However, it doesn't have to be the case. I can actually have a fundamental theory that forbid this term, okay? And we have many theories that forbid it. For example, that we impose something called lepton number, and we impose lepton number on the theory. That's actually related to the thing I wanted to talk next, okay? So I want to talk next on a little more about symmetries and how they are related to the difference between a standard model and the standard model. So as I said, we have those symmetries. Those symmetries are the symmetry that we impose. Those are the input, okay? Remember, you go to the website, you put them in. That's what you put in. It's up to us to decide what they are. But then, when things come out, you can have other types of symmetries. Those kinds of symmetries are output of this process. They are not input of the process. Okay, so they are fundamentally different between those two types of symmetries. Input symmetries, that we say they must be there because we impose it, because that's the way I do model building, and output that come out, okay? And there's two types of symmetries that come out when we do it, okay? And I want to talk about them one by one. The first one is what we call an approximate symmetry. An approximate symmetry. An approximate symmetry. And an approximate symmetry is basically tell me that it's not exactly a symmetry, it's almost a symmetry. What does it mean? It means that I can somehow define some small parameter, and it's better be a dimensionless small parameter, such that if I take this small parameter to 0, the symmetry would be exact, okay? However, it's not totally the same, okay? And we all really familiar, and usually we make it as a joke, as you remember from kindergarten, the jokes when you teach like, some advanced topic, and as you remember from kindergarten. But this you do remember from kindergarten. Do you remember in kindergarten that you get these two pictures that are almost the same, and you have to, help John find right? And you have to find like small differences between the two pictures, you remember? So how did you, as a kindergartner, when your mom said, hey, what are you doing? I assume you said, hey, I have here an approximate symmetry between the two pictures, and I want to find the deviations, okay? So an approximate symmetry is something that really almost look the same, but there's slight small changes between those, okay? Let me give you some example in the standard model of an approximate symmetry. For example, one that is kind of known is isospin. What is the isospin symmetry? It basically tells us that the proton and the neutron are the same. You can exchange a proton and a neutron and nothing changed. We say, well, is it true? And if you look about the strong interaction, if you look about nuclear physics, then basically we know that the neutron-neutron and neutron-proton force inside nuclei are basically the same. When you look at the mass is basically the same. That's why in chemistry we call it atomic number. Atomic mass, right? We don't distinguish between proton and neutron in atomic mass. Yes? So if you ask a chemist said, I don't care, just tell me how many total nuclei I have, I tell you the mass of this isotope, right? So for chemistry, it is almost the same. But it's not exactly the same. They have a very little difference in mass, and they have also electric charge that is different. So they are not exactly the same. Okay? Good. So let me ask you now the following question. Is isospin? So I assume you all heard about isospin before. Yes? Is isospin an approximate symmetry in a standard model or only in the standard model? In the standard model, absolutely. In a generic standard model, that's not going to be the case. The reason that we have isospin in the standard model is a specific value of the parameters. The reason that we have isospin is the fact that the mass of the quarks, of the up-down quarks, are much less than the confinement scale of QCD, and therefore the mass of the proton and the neutron are almost the same because most of it come from the QCD interaction. Okay? In a different world with an up and down quark different, it will be different. Okay? So the approximate symmetries, and that's a general statement, all the approximate symmetries of the standard model are there because we are talking about the standard model. They are not generic for any model. And therefore they are important when we try to understand the higher dimension operator and the effective field theory that build them. The other type of symmetries that can be the output of this story, we call an accidental symmetry. Accidental symmetries. So what is an accidental symmetry? An accidental symmetry is somewhat unfortunate name for the following phenomena. It's a phenomena that when you take some system and you truncate it at some point, you gain a bigger symmetry than what you start from. Okay? And you're very, very much familiar with this phenomena. And for that, let's take for the simple example the pendulum. Okay? We all know the pendulum, yes? And one very important result of a pendulum is that you know that the frequency is independent on the amplitude. We know this result? Yes. Okay. Given the fact that this is such a result, there must be a symmetry, an underlying symmetry that is there. Okay? Another thing that you also know that this result, that the frequency is independent of the amplitude, is only correct when we keep the harmonic term. When we go to the theta to the 4, this is not there anymore. You remember this thing? Okay? So that somehow the system gain an extra symmetry when we truncated the harmonic term. Okay? Let me write it. I mean, this is, when you write the potential for the, it's cosine theta. Yes, that's the potential for the pendulum, and then you expand it, and then you say it's theta squared over 2 minus, it's minus here, plus theta to the 4 over 24. Yes, plus whatever. Yes? When I keep only this term, the amplitude is independent, the frequency is independent on the amplitude. When I add this one, I lose this property. Okay? Why? Because when I truncate here, the system gain an extra symmetry. Anybody know which symmetry we gain? The simple harmonic oscillator, I mean, it's not the simple harmonic. The pendulum, I mean, one of the classics example. Definitely, first year physics, high school physics, right? What is the symmetry that we gain when we truncate? Anybody know what is the symmetry that we gain when we truncate the potential at the harmonic term, when we only keep this term in the cosine?
Scale invariance?
Scale invariance, very nice. If I was teaching, I said I'd be quiet now for 2 minutes and let you, but it's scale invariance. So what's happened, the symmetry that we gain are scale invariance, which is defined as x go to lambda x for lambda not equal to 0. And basically is you rescale all your variables. You take all your x's and rescale them. Scale invariant is a symmetry when you have a Lagrangian where all the powers of x are the same. Okay, and if you look at the simple harmonic oscillators, it has scale invariant in it because the kinetic term is x dot squared and the harmonic term is x squared. Yes? So it's mx dot squared plus kx squared over 2. So you see everything is x squared. So when I actually do x go to lambda x, nothing changed. It's just like multiplying everything by a constant. And multiplying everything by a constant doesn't change the equation of motion. When I add the extra term, okay, this extra term, the theta to the 4 term, now this symmetry is not there anymore. Yes? Okay? And that's actually the reason why the frequency doesn't decay on the amplitude. And it's kind of nice because the amplitude is really something that has to do with it has a scale. And scale invariant basically tell me there's no fundamental scale in the theory. So it's kind of a cool, nice understanding. One extra deep thing about simple harmonic oscillators that I'm happy that is new for some of you. Okay? But coming back to my point, is that we see how we gain an accidental symmetry. An accidental symmetry we gain by truncation. When I truncate, the system has an extra symmetry. Are you with me on that? So let me ask the following. Are these accidental symmetry, are they a result of a standard model or the standard model? A standard model. So that's a fundamental result of the truncation. When I truncate, I don't care about the value of the parameters. You see in that simple harmonic oscillator, I don't care about the value of m and k. When I truncate, I get this extra symmetry. Okay? Good. Now in the standard model, we have both approximate symmetries and accidental symmetries. Approximate symmetries are, for example, isospin symmetry. There's a few others that I'm not going to discuss much. The accidental symmetries of the standard model are very well known. They are called baryon number and lepton number. So the accidental symmetry of the standard model basically tells us that there's extra conserved quantity that we call baryon number, and the proton and the neutron carry baryon number, and the quarks carry baryon number, and therefore the proton cannot decay. Because if the proton, there's nothing lighter that is a baryon. So the fact that the proton is stable is not fundamental, just like electric charge conservation. Electric charge conservation comes from the symmetry that we impose. It's the input. Yes? So if we find that electric charge is not conserved, we know that our input is wrong. Yes? However, baryon number and lepton number conservation, the thing that protect the proton, they're not fundamental to my definition of the theory. It's only due to my truncation. So if, say, we find that the proton decay, what we conclude, we will not conclude that the model is wrong. What we conclude that the truncation was done too early. Okay? So it's fundamental difference between those two. And therefore, we all hope and believe, or whatever you like to say, that someday we're going to find the proton decay, and then we'll understand, hey, we understand the deeper, more higher dimension operators in our theory. Okay?
Maybe a comment, I guess in a different community, what you call approximate symmetry will probably be called accidental symmetry.
Really?
And what you call accidental symmetry will probably be called emergent symmetry. So the reason I would say the approximate symmetry in some sense is accidental is because it's a result of the choice of the parameter.
I totally agree.
So that's accidental. But what you call accidental symmetry is actually a robust consequence.
I totally agree with you.
And that's why it's called emergent.
I really like it. And then I say it's an, I said it's an unfortunate choice of words, but that's how we use it in high energy physics. It's definitely not my definition, but I really like this. We should have go out and do a revolution. This is approximate symmetries, and these are emergent, and this is accidental, right? But this is this is the way in high energy physics we are calling them. But I totally agree with you. It's really. This is only because the specific value of the parameters. In this sense, it's accidental. It's not, and this one is much more robust because of the truncation.
Although it may look accidental.
That's right.
But the moment you need to understand that the theory is not accidental.
I guess there's in the history of science, there's so many places that we choose a word that later on, when we fully understand, we just say that was a bad choice of words, right? And then you start with that. So I guess we'll start with that.
Like virtual particles.
Like effective field theory.
Okay. So let me move on to discuss the flavor structure of the standard model. And let me say that I kind of jump between saying the standard model and nature. And it's not a trivial thing, but the standard model basically explains nature. So I'm not going to kind of make a difference between them at this level. Okay? So I say, oh, the standard model do that. That's implied that that's what we see in nature. It's basically the same story as of now. Okay? So what we have in the flavor sector in the standard model, it's the fact that we have 3 different copies of the fermions. And what we find is the following interesting phenomena, is the fact that there's always, we can have transition between those different quarks, okay? So if you take just electromagnetism, for example, forget about the weak interaction, then once you have a specific quark, this specific quark is always there, okay? If I start with an electron, I'm always going to have 1 more electron than positron in my theory. So I can have 5 electrons and 4 positrons. But the difference between the electron and the positron will be always 1, okay? It's a conserved quantity, okay? The same would be with quarks. If I forget about the weak interaction, if I start with a theory, let's say that I have 1 strange quark, okay? And I do whatever you do, and it's not the weak interaction, at the end of the day, you always have 1 more S than S bar, because the quantity is conserved, okay? However, the weak interaction, actually, this quantity is not conserved anymore. I can start with an S quark, and I end up with something that has 0 S quarks, okay? For example, S can decay into a U, and an electron, and an antineutrino, okay? That's the way most of the S quark in nature decay, okay? So we see that we say flavor is violated, okay? Flavor would have been conserved if the number of S's would be always the same. And now we see that it's not. Okay, that's the meaning of flavor violation. Yes? And the whole point of flavor violation is part of what we call the flavor structure of the standard model. It's talking about how all these flavor numbers are violated and how things are happening. Okay? Good. So now, it's turned out, when you go through the algebra of constructing the Lagrangian, that all of the way flavor is violated in the standard model, it's come only from 1 specific point. And I want to emphasize, it's far from generic, okay? It could have come from many, many different places, but it's turned out that the way we built our model, there's only 1 place that this is happening, and that's so-called the CKM matrix. The CKM matrix is definitely one of the most famous matrices ever created, okay? Kabibo, Kobayashi, and Maskawa, that's the name of the people who were involving in proposing this matrix. And let me explain what is this. What is this matrix, okay? So this matrix is actually appear in the coupling of the W boson, which is the charge boson of the weak interaction, into the quarks, okay? So the way it goes is that if I have an interaction of the following, let me describe this interaction. So this decay actually goes through the W decay to the W boson, and it's described by the following Feynman diagram. Okay, here I have an S, here I have a D, and here I have an electron and a neutrino. And the coupling of the W here, I have a coupling between the S and D and the W. Okay. Thank you. And I keep talking and talking. It's like so wrong. Thank you. And what we have here in this vertex, I have the G. Remember, G was the coupling constant of the SU2, and the W is part of the SU2W. Again, I didn't get into the details. And then on top of it, we have here some matrix element that we call VUS. And what is this VUS? VUS is some element, okay, that is non-zero that tells me there's actually a connection between the U and the S quarks, okay? And this V is what we call the CKM matrix element. The CKM, V is the CKM matrix, and VUS is the specific US matrix element of this matrix, okay? Good. So what is this matrix? Basically, it's some matrix that measures some misalignment between 2 different bases. And here, quantum mechanics, all of us should have enough intuition from quantum mechanics. In quantum mechanics take, you have two different bases of two different operators, right? If they are not commuting, when you diagonalize one operator, the other one is not diagonal, okay? And in principle, there's a matrix that rotates between those two. Yes, I can have one diagonalized and the other not, or the other way around, and there's some matrix that kind of connect between those, okay? So that's what we have here. When we actually do the whole process, turn out that we have three matrices, okay? And the three matrices are the mass matrix for the up-type quarks, mu, ij, the mass quarks for the down-type quarks, ij. They both come from the interactions through the Higgs boson, and the coupling of the W, this one, that is G, Vij, okay? So there are three matrices. And it's turned out that we can diagonalize at most two of them, okay? And we can choose which one to diagonalize, but it doesn't matter. The physics is such that there is some violation of some conserved quantity, because not everything is commuting, okay? In practice, what we choose to diagonalize, we should diagonalize these two, because it's kind of nice to work in a diagonalized mass basis, because we like to know the mass of our particle. It's kind of nice. I mean, we don't have to, but it's kind of nice that we work in the mass basis. So we diagonalize those two, and then this one is not diagonal. And the fact that this one is not diagonal tells me that flavor is violated, that I can have flavor changing, okay? By the way, for neutrinos, usually we actually choose to keep this and this diagonal, and this one to be non-diagonal. The difference is the way we are doing the experiment with neutrinos are a little different than the way we're doing with quarks, and that's a better basis. However, as we all know, a basis choice is just a basis choice. Okay, it just makes your life easier to do calculation. There's no fundamental physics in it. The fundamental physics is the fact that I cannot diagonalize all three together. Okay? Very good. So what we learned something very interesting. We learned that the standard model, when we talk about flavor, is far, far from unique. Okay? So in general, I can build up models where flavor is violated everywhere, right? I can write many, many, many different ways that one flavor can move to another. However, in the standard model, the way we built it, it's very confined. It's only in this one matrix. All the flavor come in this one matrix, okay? So if I know this one matrix, I know everything about flavor transition, okay? So the standard model is far from unique in this sense, okay? So given how important this matrix is, let me spend a few minutes about this matrix. So it's a 3x3 matrix. The reason that it's 3 has to do with the fact that we have 3 copies of the fermions, and it's a unitary matrix. A unitary matrix, again, it's not surprising. It's just a basis rotation. Basis rotations are always unitary, right? And it's described by, here it's a little bit surprising, it's described by 4 parameters. Now it's a little bit surprising because how many parameters a 3x3 unitary matrix has? It has 9 parameters. Yes, it has 3 mixing angle and 6 phases. But somehow, and again, I'm not going to do it, but I love to do the counting. 5 of those phases are unphysical, and only 1 of these phases is physical. So we have 3 mixing angles and one phase that parameterize it. Okay? And then we went out and measured them. And when I say went out and measured them, that's something that it's like 30 years of, I don't know how many people working so hard to do it. But after 30 years of work, we measure it, and we find basically something like this. We find that this matrix V, I write it like this. It's UCT DSB. Very roughly, okay, the value of these parameters, as I say, just a general unitary matrix, okay? The value are roughly 0.97, 0.22, 10 to the minus 3, 0.22, 0.97, 0.04, something like 10 to the minus, maybe a little more precise. 4 times 10 to the minus 4, and that's 9 times 10 to the minus 4, 0.04, and 1. Okay? So I'm just telling you an experimental fact. You know, you just go out, measure it, and that's what you find. Okay? And if it's the first time that you see it, then you should just anybody see it the first time? How many of you saw these numbers the first time? Don't be shy. Yes? Okay, great. One of you. Can you tell me, so what your initial reaction about this matrix? That it is?
Really diagonal.
Almost diagonal, right? It's
almost identity.
It's almost the identity. And it's unitary. So if it would be diagonal, it must be a unitary matrix, okay? So the thing to conclude is it's far from generic, okay? It's the standard model. In a standard model, this matrix will be a generic unitary matrix. A generic unitary matrix would not look something like this. Do you see that this one is almost, it's almost the unit matrix, okay? The diagonal is almost 1, and the off diagonals are very, very small, okay? So what we've seen here is something really interesting that we see in flavor physics, okay? Not only that, the way we built up the standard model, we built up such that all of flavor violation come from one source. This source happened to be very far from generic. It's almost diagonal, okay? And the small numbers that kind of make it non-diagonal. If you like, the change between generation, the change between the different copies, which corresponds to off-diagonal term, is very, very small, okay? So see if I want to connect the first and the third generation. Say I connect the U quark with the first generation quarks with the B quark. With the third generation quark, it's 4 times 10 to the minus 4. I'm not sure if I remember the number correctly. But it's extremely small. Okay, I can calculate it, but not on top of my head. Okay, or we can look it up. Okay? So we learned something interesting. Okay? The standard model is far from generic. A standard model is far from generic. And this standard model is even more far from generic than a generic standard model. So the flavor sector of the standard model, or the flavor sector of nature, is very far from what you expect from a generic effective field theory point of view. And that's something that you already kind of mentioned when you asked me this question, is that if I just think, oh, I just write my most general operator, it's definitely not going to give me what we see in nature. So there must be something deeper going on, and we don't know what it is. I mean, but that's kind of one of the interesting things that we are.
You said 3 angles and a phase.
Yes.
Is the phase included in?
No. So here I wrote the absolute value.
The absolute.
And actually, when you let me say a few more things since you asked. Let me say a few more things. Is that because of this structure, Wolfenstein say, oh, you know, when you have such a thing, it's called for an expansion. Okay. So Wolfenstein decided to call he wrote the CKM as an expansion in a small parameters. And the Wolfenstein parameterization, it have 4 parameters. One of them is small, and 3 are suppose order 1. And you expand in the small parameters. And when you explain in the small parameters, it goes something like this. Lambda cubed, and here there's something like a rho minus I eta. And here is minus lambda, 1 minus lambda squared, 1 minus rho minus I eta minus a lambda squared, and 1. So the point is, Wolfenstein, what he did, he said, oh, giving the fact that it look almost like a unit matrix, let's expand in the small parameters. And he take the full parameterization that we know exactly, and we wrote an expansion. Okay? And when you write the expansion to leading order, you find that CP violation, I already said CP violation, I didn't mean to yet, but I mean, the phase appear only here, this I and this I. Okay? The phase only appear in the 1,3 and the 3,1 element. It doesn't appear in other places. And in general, when you do it, there's actually 5. So you can eliminate it in 4 elements, but the maximum you can do is 5. You think this one will do better for me? Yeah. Okay? And let me say something kind of, again, semi-philosophical about this point. Okay? We do have an exact expression for the CKM. And what Wolfenstein did, and everybody said, like, wow, Wolfenstein did something amazing. He take an exact result and wrote it as a non-exact result. Okay? Usually, we like to go the other way around. But the reason is that this is so important is because so many times when you actually approximate something, you get some physics out of it. And the idea of knowing how to approximate things is so deep in the way we like to do physics, okay? So people do use the Wolfenstein parameterization, which is an approximation, although we can have the exact result, okay? So let me say one more thing about this I, the fact that it's not real. This has to do with CP violation. CP violation has to do with the difference between matter and antimatter. And we know that in nature, there's a small difference between matter and antimatter, okay? And in principle, you know that the electron is not fundamentally in all ways really a mirror image of the positron and the electron are not mirror image of each other, okay? And this, in the standard model, has to do with the fact that this is a complex matrix, okay? And what we see here is that the complex number appears only in the small parameters. I forgot here lambda. It's always appearing those which are the very small numbers on the corners. And therefore, that's why we kind of say that CP violation in nature is a very, very small phenomena, that CP is an approximate symmetry of nature in that sense. And we understand where it's coming from. It's coming from the fact that it's come together with those small parameters, and a priori we have no explanation, we just say that's what it is, okay? Okay. Any more questions? 15 more minutes. So I will move to another topic. Not totally, but I still want to talk about flavor changing. So we are still trying to understand like the flavor structure of the standard model. And one thing that I was just telling you is that everything comes from this V, and V always connect to the W boson. And W boson, I should have said, I forgot, is charged. It's the only gauge boson that is charged under electromagnetism. It has an electric charge +1 in nature, okay? And what we find in the standard model that all those other bosons that can mediate forces do not change flavor, okay? And in particular, in the standard model, there are 4 other bosons that mediate forces. There are the photon, the gluon, the one for the strong interaction. Then we have the Z. The Z is the heavy boson for the weak interaction. And we have the Higgs field, the Higgs particle, that is also a boson and can also it's also coupled to fermion. But somehow, what we find out, again, that all of those do not change flavor. The only one that do change flavor is the W+. So this one, violet flavor, and this one, not. Okay, so we have this kind of thing. So somehow, again, it's by construction, and the construction of the standard model is far from generic. It's far from generic in the following sense, that the neutral gauge boson, the neutral bosons conserve flavor, and it's only the charged one that violate flavor, okay? So we talked about the fact that flavor is conserved by electromagnetism, etc. That means that the photon is conserved flavor, okay? And it's conserved by the strong interaction. That means that the gluon is conserved in flavor. So let me spend a few minutes on, yes?
Since all of those are electrically neutral particles,
yes.
How could they actually change flavor, right? If I want to go from an S to a new U, for example.
Yes, so for example, the thing would be something like this. I have an S, and here I have a D, and here say I could have a Z boson because they have the same electric charge. Okay? And that's exactly what I wanted to introduce. Such a thing, it's called, it have very famous acronym, FCNC. FCNC stands for flavor changing neutral current. Okay? It's a flavor changing coupling to a neutral gauge boson. And that's different from what I had before. That was an SU and a W that we call FCCC, stands for flavor changing charge current. Okay? So flavor changing charge current is something that we see in the standard model, that we have in the standard model. This one, we don't have in the standard model. We do not see such a thing in the standard model. So what we see in the standard model and in nature, we see something again. Flavor is far, far from generic. It only occurs in the charge current interaction, and it occurs only through one specific matrix. And this one specific matrix has a very, very non-trivial structure. Okay? Good. So let me go to the very last part when I'm kind of building up and telling you how much the standard model flavor structure is far, far, far from generic. And that's why we actually going to connect it to effective field theory on Friday. And the point is as following. So I told you that you have flavor changing charge current, but not flavor changing neutral current. However, once you have flavor changing charge current at tree level, you will get flavor changing neutral current at one loop. The way to think about it is that when I exchange I exchange a W plus and then a W minus, effectively I exchange something neutral. Yes? So I can get flavor changing neutral current by exchanging two charge current gauge boson, and that happens at one loop. Okay? So flavor changing neutral current is not there at tree level, but it's there at one loop, and of course it's also there in nature, but it's extremely suppressed and extremely small. So I want to give you one example of what we have, and I want to talk about a phenomena that is called meson mixing, and I want to talk about, as an example, of something called KK bar mixing. Okay, KK bar mixing. And this is a phenomena that involves flavor changing neutral current. A kaon is something that's made out of an S bar and a D quark, and a K bar made out of a D bar and an S. Okay? So that's a K, and that's a K bar. Okay? If you don't know, I'm just telling you. Now, in principle, going from here to here is a neutral current, you see, because here I have all the quarks have the same charge. So how can I go from here to here? The diagram is like this. It has two exchanges of a W propagator. Here I have a W and a W. Here I have a U and a U. So here the S bar become a U bar or a C bar or a T bar and become a D bar. And here the D become either a U or a C or a T, and then it go into an S. Okay? So I have here a total of 9 diagrams because I have 3 U's here and 3 U's here. So I have 9 diagrams. I have to add those 9 diagrams up. And when I add them and I calculate them, then I can actually calculate the effect of KK bar mixing. And the effect of KK bar mixing give us a mass difference between the two mass eigensets of the kaon system called K long and K short. And we went and we measured it. Okay? And when you do the calculation, and that's the last formula I'm going to write today, we find the following result. And what is so nice about this result is it actually agrees with the experiment. Okay? And the result is as following. Delta M K over MK, so I normalize the mass difference over the average, is equal to some stuff that are not so important. I'm going to explain what all of this in a minute. I really need all the blackboard. Times mk squared over mw squared times VCS VCD absolute value squared times mc squared minus mu squared over mw squared. Okay? I know usually you should not write formulas on when you have on lecture you should, but when I have so little, so why did I bother and write such a long formula where part of this we don't even understand? Because I really want to get to my very final point about flavor physics through this formula. Okay, so let me explain what are all those factors. Okay, these factors are some parameters that we know their value. They're called hadronic physics, and that is the less interesting part. That's called hadronic physics. And it's extremely interesting, but not for this talk. Okay? What is this? What is g squared over 96 pi squared? And for all of you who are experts, and I know there's real experts here in doing loop calculation, whenever you see g squared over pi squared, you know it's coming from higher loop. So the fact that this is a loop calculation, or when you do loop calculation, you get g squared over 16 pi squared. Okay, there's another factor of 6, but it's not very important. Okay, so this is loop. If the fact that this comes from one loop is manifest in this factor. What is this factor? This factor basically tell us that it all comes from the weak interaction. The relevant scale of the process is the mass of the kaon, but the fundamental masses that run in the loop are the mass of the W. So that's basically tell us that it really comes from a very short distance physics, very high energy physics. So that's just the fact that it's the weak interaction. The weak interaction. What is this? This has to do with the CKM, okay? And in particular, while VCS is a diagonal element of the CKM, VCD is an off-diagonal term. And by now we all know and familiar with the fact that off-diagonal terms are small, okay? So this is what we call the CKM suppression. And what is this? This is MC squared minus MU squared. Just to give you a number, MC is roughly 1.3 GeV. Okay, MU is few MeV, so it can be neglected. So it's MC squared is like 1 GeV over MW. MW is 80 GeV, roughly 100 GeV. So this factor is about 10 to the minus 4. Okay, and this factor go under the name of the gene suppression. Okay, so what happened when you actually look at the number, at the formula, you find that the formula made a lot of small numbers. Okay, and numerically this value is 7 times 10 to the minus 14. Okay, 7 times 10 to the minus 14, which is a small number. Okay, it's amazing how we can measure it. We can measure it through quantum oscillation, where you can measure very, very small numbers. Okay, and theoretically we understand this small number as a product of many small numbers. Okay, this one is not a small, this one is order 1, but all the others are small numbers. Okay, this is a loop factor. Okay, 1 over 96 pi squared is like 10 to the minus 3. Yes. The weak interaction, this is like MK is roughly half a GeV. So that's another factor of 10 to the minus 4. This VCB is, this VCD was 0.22. So that gives me another small suppression. And this one gives me another small number. So there's many small numbers. Okay?
Why do you only have the charm coordinate? So you have UI and UJ, right?
Yeah, so you can also need the top. Yes, so I didn't write the top.
Okay, but then
and the reason that I didn't write the top because the top has, this suppression for the top is so big that it's not very important. Okay? And actually if I do the same for BB bar oscillation, I will only keep the top. So that's some approximation that I was making.
But what about the U in the intermediate?
Oh yeah. So that's why I have MC squared minus MU squared. So this is MU. Sorry for my handwriting. Okay, so it's MC squared minus MU squared.
In the CKM matrix, why is there no DU?
So here I use the unitarity of the CKM to eliminate it. So I did a lot. There's some stuff that I did. Okay, but the point, and that's kind of where I wanted to end this lecture. Wow, 2:59. Yes, is to leave you with the following thing. Okay. I didn't get into all those factors, but the point is that the flavor structure of the standard model, which agree with nature, is really far from generic. It's the standard model plus a standard model. So already the standard model is very specific, okay? And then you do this standard model, you find that it's really far from what you would expect from a, just, write your theory, what you expect. You don't expect those kind of things. And you have to work hard to understand why we have these extra 4 suppression factors. Okay? This one is generic to S standard model because it's the loop, it's the fact that it's there. Okay? This one is kind of the standard model because the mass of the W is so heavy. And this one is fundamentally small flavor parameters. Okay, it's the fact that the mass of the charm is very small compared to the mass of the W, and that the CKM is almost diagonal. Okay, so let me conclude by saying the following. Okay, hopefully, I know if you're an expert, all what I said is very well known, so I didn't catch you. But for the non-expert between you, hopefully, even if you, of course, I had to go around a lot of details. The point is that I hope that we understand that the flavor structure of the standard model that tell us the different things is far from generic, okay? And it's this fact that is so far from generic, and we fully understand it now, okay? When we try to understand what's going on beyond the standard model, becomes very important when we try to go behind it, okay? So we leave it like this for today, and on Friday I'll continue with what's going beyond it.